Hello everyone, this is Nandini S from Food Technology Department. In this video, we are going to see about the physics behind ice cream. Let us start with the fact. Americans eat more ice cream than anyone else in the world, about 35 pence per person per year. Ice cream as an industry in India may be said to have started in 1960s. Today, ice cream is considered as a luxury food item. The production of ice cream in 1966 was estimated to about 0.7 percentage of total milk production and 1.3 percentage of milk used for the manufacture of dairy products. Now you may wonder, why should you bother with the science? Because it will actually help you to make better ice cream. And ice cream is actually quite a complex and multifaceted composition. It should be solid, yet soft, and should preferably stay that way while melting slowly. If you would simply put a batch of ice cream in the freezer, you would not end up with ice cream, but with a block of hard frozen solid cream. Molecular gastronomy has become quite popular in recent years. Understanding at least something about the physical and chemical aspects which turn your ingredients into delicious ice cream will not only add to your general knowledge about the world but will also give you something to talk about over your next scoop of ice cream. Most importantly, it will help you to prepare your own ice cream in a better, more mindful way, drastically increasing your success rate in the kitchen. The upcoming contents are ice crystals, Ostwald ripening, avoiding large crystal, phase transition, freezing point depression, production of ice cream. Ice crystal. Everyone loves ice cream, but what makes good ice cream? For most people, the answer seems to be how smooth and creamy it is. The perceived smoothness seems to increase as the size of any solid particle in the ice cream decreases. This is especially true of the ice crystals. So, a good ice cream has the smallest possible ice crystals. This leads to many questions. For example, why do ice crystals form? Crystals form when a particular species of molecules is given the opportunity to align with other of those same molecules. Simple thermodynamics tells us that smaller crystals are less stable and will slowly disappear as larger crystals grow steadily larger. This process is known as Ostwald ripening. So, commercial ice cream manufacturers have to find ways to slow down this ripening process. Some of the best solutions are using stabilizers that coat the surface of ice crystal so that it reduces the crystal growth as they effectively reduce the liquid solid surface energy and stabilize small crystals. And an interesting thing related to this is these antifreeze proteins are found in fish that live in the cold polar waters. So, understanding of how fish evolved and survived in such cold water without the formation of ice crystals in their bodies has a direct link to the production of ice cream. Traditional machines used in production of ice creams simply scrape growing crystals. The crystal size then depends on how well the scraper fits the surface, how stiff and sharp it is, how fast it rotates, how quickly the mixture is freezing, and how long it is held before serving. A newer type of machine, the Pacojet, drives a rapidly rotating scraping blade into a solid block of ice cream mixture at a low temperature, approximately 20 degrees Celsius, so that it advances around 0.001 millimeter per revolution. This shaves crystal fragments that have a size typically around 0.005 millimeter. Even smoother ice creams can be made by freezing at very low temperatures using liquid nitrogen as the coolant. By nucleating crystals at very low temperatures, very small crystals can be stable so that it is possible to have an ice cream with ice crystals that are smaller than 0.001 millimeter. Phase transition, freezing point depression. In fact, the attempt to measure the sizes of such crystals has the potential to develop new methods of investigating the physics of phase transition in confined spaces. When the ice cream changes phase, it will change from a liquid to a solid. However, we will use salt to make this more difficult. The ice cream will stop before it freezes into a solid. This process of lowering the freezing point by adding salt and water is known as freezing point depression. The freezing point is mostly lowered through the addition of sugar. Sugar dissolves in the water and this way interferes with the crystal formation. This physical phenomena is the core of many ice cream machines. This is the phase diagram of sucrose and water. It is also called practical phase diagram. Since we are talking about ice cream here, we will only discuss one region. Take a sugar solution with 20% sucrose at minus 18 degrees Celsius. We end up in the ice in liquid region. This means that there are both pure ice crystals as well as a solution of sugar. This is what makes our ice cream nice to eat. Not too many ice crystals and sufficient liquid sugar solution which is soft. Production of ice cream. Ice cream is made of five basic components: air, sweetness, fat, ice crystals, and other solids. Air. Typically, air makes up 30 to 50% of ice cream's total volume. Air prevents an overly sweet flavor while creating structure. Sweeteners. Sweeteners are crucial to an ice cream's flavor and quality because cold foods tend to numb your taste buds, making them less sensitive to flavors. To address this, more flavorings must be added. Fat. The main reason why ice cream tastes so devilishly delicious is its high fat content. Ice cream must be at least 10% fat, and this fat must come from milk. Now, with all these components, it's time to make ice cream. First, the base is prepared. Milk, cream, sweeteners, and other solids are mixed together. Next, the base is pasteurized to eliminate any dangerous bacteria. The base moves on to homogenation. Homogenation is the process in which the fat droplets in the base are broken up and dispersed. The problem with fat is that it does not get along with most substances, including water, which is in basically everything. Keep the fat and water in ice cream together, an emulsion must be created. Each fat droplet is then coated with a layer of milk proteins, one of fat's few friends, which prevents the fat from clumping together. The base cools to fridge temperatures and it is given time to age and mature, greatly improving the texture, smoothness, and stability of the ice cream. The base is pumped into a metal barrel surrounded by a refrigerant while a stream of air is introduced into the barrel. Then the mixture is churned, creating ice cream. Finally, the ice cream is put in the freezer until it is ready to eat. Hope you came to know about the physics behind ice cream. Thanks for watching.